All right, in this problem, we see that there are two conductors carrying the same current. The direction of the current in the internal conductor is upwards, as you can see here, which is this one. And for the outer conductor, it's going inwards, and the magnitudes are the same. Now, in the first part, they have asked you to find out the magnitude of the magnetic field at the surface of the inner conductor, right? So that means you have to take the total current that's flowing in this region, right? Which is basically the current I, right? All right. Now for the part A, we are gonna use the magnetic field formula from the Ampere's law, which is this one, and in this case, our R is basically A, right? Because we have to find out the magnetic field at the surface of the inner conductor. Now, uh, what's the value of I, since we're taking the complete current flowing through this region, right? So our value of I would be 200 milliamps, right? So now we'll just plug in the values right now. So which is basically mu naught times 200 milliamps. So that means it's like, be careful of the units, right? And it's 2 pi, and A in this case is 1 centimeter, so we have to convert it into meter, right? So it's just 0.01. So now we'll end up having 4 times 10 power minus 6 Tesla, right? So that's the value that we are looking for. Now in part B, they have asked you to find out the magnetic field in the region for the radius greater than C, right? So that means they're asking you to do find, like, if you enclose an area that I have drawn, this one, right? So for this one, radius is greater than C. Now remember, from Ampere's law, it should, my magnetic field should basically be given by this same equation. In this case, my R is greater than C, but the I should be the I enclosed by my area or the line integral, right? So now what's my I enclosed? My I enclosed is the current I going upwards and the current I going downwards, right? Because I'm enclosing both the currents, and since the magnitudes are same and both the currents are flowing in opposite directions, so therefore my net current will be 0, right? So what's my magnetic field for R greater than C? It's 0 Tesla, right? Okay, now for part C, they have asked you to find out the magnetic field at the distance 3.5 centimeter from the center of the cable, right? So that means, like, it is between B and C, right? It is somewhere between B and C in this region, right? So you know your R. So your R is basically 0.035 meter, right? Be careful of the units. And now, yeah, all right, sorry. So your radius, so you have to take an area which is enclosing a part of this circular region, right? So it's enclosing basically a part of the circular region, so between B and C. So it's not enclosing the entire outer current, right? It's not enclosing the entire outer current. So it's basically like, if I draw, this is my outer conductor, right? If I draw my outer conductor, so my internal radius is, let's say, given by B, right? And my external radius is, let's say, given by C, right? In this case, it's given by C. So now I have to take an area which is not enclosing. If it was enclosing the entire region, so I would have current I, right? But I'm enclosing a part of the area, right? So that means I'm enclosing a part of I, right? In this case, maybe you can consider negative I, because this I that I'm considering is going downwards, so I can consider this as my negative I, and the current going upwards I can consider as my positive I. All right, so therefore my net magnetic field equation should have the same form, right? I enclosed divided by 2 pi r. In this case, what's my r? It's this 0.035 meter, right? Now, what's my current in enclosed? Now, remember, I am enclosing uh, the entire of the positive current, right? Because my area is enclosing the complete region, internal region current, right? So I'm encompassing basically the total internal current of the inner conductors, which is positive I, and I'm also enclosing a part of negative I, right? So now how much I'm enclosing the negative current, right? So that depends upon the area of the difference, right? If my total area of this ring my total area of this ring should be pi c square minus pi b square, right? So now I am enclosing a portion of it. So how much I am enclosing? So now basically I am enclosing, I can say c square minus b square, that's the total area of the ring. So now I am enclosing a part of the ring. So which is basically, I can say it's c square minus r square, right? Because my r is between, in this case, my r is between b and c, right? So yeah, so now once you plug in the values, you know all the values. So once you plug in the values, you will get B is equal to basically 6.12 into 10 power minus 7 Tesla. All right. Okay. Now, for the last part, they have asked you to find out how the magnetic field varies as a function of the radius, distance from the center of the geometry, which is r is equal to 0, right? Which is r is equal to 0 to r is greater than c, right? So I can just say that, okay, now if I draw it, all right, so if I draw it, then let's say I have to draw the graphical representation, right? So what I do is like I draw the two axes. Now remember to put in the correct units, right? So I'm looking for the magnetic field, which is Tesla. Now that's like 1 centimeter. This is 2 centimeter, right? This is 3. This is 4. All right. Now, yeah. So now, yeah. So you see from 0 to 1, right? So 0 to 1 centimeter means basically you're coming from the center, right? You're coming from the center, and then you are encompassing like a portion of the internal conductor. Let's say if I am considering this is my internal conductor and my radius is a, right? So the more the radius, as I increase my radius, I am encompassing basically more area of the current, right? So basically what I am doing is I'm encompassing a current which is proportional of the total area, right? This much. So basically when my radius is, let's say when my r is 0, so I am encompassing basically 0 current, right? So what's my B? It's going to be 0 Tesla, right? So when I'm at the center, I'm starting from the 0 Tesla, right? Now for this current, right? So for this current, my B, so basically if I consider my R is 0 to 1, so my B is basically mu naught 2 pi R, right? Times this current, right? So which is basically R squared by A squared times I. Now these are will cancel, so I will end up having mu naught 2 pi A squared Ri, right? So you see it's a linear dependence with R, right? It's a linear dependence with R. So basically this line would have a linear dependence with R. and at 1 centimeter, remember, which is at the point A, we found out our magnetic field value, right? We found out our magnetic field value, which is 4 microtesla, right? So this should be my 4 microtesla. And then for this region from 1 to 3 centimeter, so that's basically let's say the region between the internal and the external conductor, which is this region, right? So for this region, I'm just encompassing only the internal current I, right? So for this one, so let's say for greater than A, less than B, right? So for this region, my B should basically look like this, right? So in this case, you see my I is constant, which is the internal current, 200 milliamps, and all the values are constant. Now my B is basically proportional to 1 by R, right? So this should have a 1 by R like dependence with distance. Now at 3 centimeter, right? So at 3 centimeter, so you can plug in the values in this equation and you'll end up finding a value which is 1.33 microtesla. Right. Now, for R greater than 4 centimeter, which is R is greater than C, remember we found in part B, it's equal to 0 Tesla, right? Because you're encompassing both the positive and negative currents. So for this region, your magnetic field has to be 0, right? Now for this region, so for this region, it's proportional to R. This region is proportional to 1 by R. And in this region is basically 0, right? 0 Tesla. And in this region, you are encompassing basically a portion of the outer current, right? So this will have basically a dependence of pi c square minus pi r square, right? It's basically c square minus b square, right? So since it has a quadratic dependence with r, and this has a, let's say, power of 1, right? So this should fall faster with distance and it should become 0 from 4 centimeter and on.